Thank you. I'm sure somebody will let me know if you can't hear me and if you can't see the screen, but I think that was okay. So what I'm going to do is going to talk about three different aspects of analyzing geophysical data and why we do it as geologists and how we do it traditionally and how we've been working within DARE and within various other groups such as the MINEX Cooperative Research Centre to use data analytics and different types of image analysis to better understand what these images are telling us. So I'll start off with just an introduction to explain why in Australia and in many parts of the world, these geophysical data sets are so important to us. And going to talk about three different topics. I'm going to talk about structural geophysics, which is the interpretation of the manual interpretation of these data sets. I'm going to talk about the work that Leoportis has been doing on trying to understand how these different data sets can be pulled apart and glued back together. And then finally, some work on how we are using machine learning, an improved version of the machine learning that we do sort of more or less routinely, specifically aimed at geophysical data. So starting off with a very large rock, this is about as big a rock as you can get. It's Mount Everest, and the dashed line is the location of a particular fault that cuts right through the top of the mountain. And amazingly, this fault is only about 16 million years old. So the entire Everest has been uplifted in the last 16 million years to its current height. And there's an awful lot of rock to be seen, and there's an awful lot of geologists that have crawled all over Mount Everest because it's you can, if you're a good climber, which I'm certainly not, you can get to almost anywhere on it and look at the geology. And just for a point of reference, the average gradient, the average slope going up Mount Everest is about 15%. And we can compare this beautiful exposure of rock with the Nullarbor, the Eucla Basin in Western Australia. This is taken from the side of the road by Google Earth. And just for reference, this is, instead of being 15% gradient, it's 150 times flatter than Mount Everest. It's got a 0.1% gradient. And the Yinhila people call it the waterless region. In English, it's Nullarbor, which means no trees. And in fact, even though I said it's got no rocks, it's actually the world's largest exposure of limestone bedrock. And there's about 300 meters of limestone. And some geologists love limestone, and that's all they really want to do in their lives. And so this is a fabulous place to look at that geology. But if you want to ask yourself the question of what's going on beneath this limestone, really you have to dig for 300 meters or drill for 300 meters to see anything at all. So this is the satellite version of that data, and the most interesting things you can see in the satellite data are there's this big east-west straight line, which is the railway that's going from Perth to Adelaide. There's a bunch of sort of squares, which are just roads. And there's not a lot of geology to be seen in this satellite data. If we look at the geology map, it's really one of the most boring geology maps on Earth. We have two different types of limestone, one of them slightly older than the other. One of them's about 15 million years old, and one of them's only a million or 2 years old. And really, again, no information. The reason there's no information is because, of course, we're looking at the same horizon all the way across what is hundreds of kilometers of Western Australia. So what else can we look at? We can look at the surface topography, and this is an image of the surface topography using data collected from the shuttle radar system maybe 20 years ago now. And the colors here refer to height. And we can see that from the black dot, which is where we've been looking north, we're going maybe 200 kilometers, and we've got maybe 200 meters of relief. So really, it's pretty flat. There's a few things going on that we'll come back to later on. So in order to get over this apparent lack of data, what we do as geologists, or what we've been doing for the last 30, 40 years at least, is we've been systematically acquiring magnetic data. So we're measuring the Earth's magnetic field from an aeroplane, flying back and forth across the continent. In fact, the entire continent of Australia has been flown for airborne magnetic data over the last generation or so. And when we do that, we can then grid the data and display it. And that's what it looks like when you look at the magnetic data. So this is an image of the variations in the magnetic field across exactly the same region. And in it, we can see that there's a lot of information of different types. And since many of you are not geologists, I won't bore you with them, but I will point out this north-south feature, which is known as the Mundrabilla Frost Shear Zone. It's up to 11 kilometers wide, going north from outside the image down through across into Antarctica, which used to be joined onto Australia. The whole shear zone, which is essentially a type of fault, is over 1,500 kilometers long, and it formed slightly over 1 billion years ago. So this is a major structure that's helped to define the formation of the Australian continent. And before the availability of these types of data sets, we really knew very little about it. With these magnetic data sets, we can map out in a continuous fashion the magnetic properties of the rocks. And from that, we can then infer something about the mineralogy. And from that, we can infer something about the types of rocks they were, but also the types of structures that are forming, such as this major fault. I said it's a billion years old, but in fact, when we look back at that digital terrain model, which I'll put back up again now, we can see that there's some structures in the digital terrain model which are exactly paralleling the magnetic data. And these structures are forming in a limestone plateau that's only less than 15 million years. And if we draw a profile across the digital elevation, we can see that there's about a 15-meter cliff across what was actually a billion-year-old fault. So this is telling us that the fault is what we say in geology is being reactivated. It's a plane of weakness that formed 1 billion years ago, and as recently as 15 million years ago, it was still actively deforming. So these are the types of data that we can get out of our types of information we can get out of our geophysical data. And when I say geophysics, in fact, there are many, many, many types of geophysics. And in this talk, I'm only going to talk about magnetics and gravity. So magnetics is measuring the magnetic properties of a few minerals in the rock. Gravity is measuring the variations in density of all the different minerals. But as you can see in this table and in the sort of wedge of the Earth on the left-hand side, as we go down through the Earth from the surface where the tree is, and this is a log scale, so be aware of that, there are many different types of methods that we can use that can look at the surface, the near subsurface, the top 100 meters, the top kilometer, the top 50, 60 kilometers, and all the way down to the center of the Earth. And what's interesting about all these different techniques is that they measure to different depths into the Earth, but they're also measuring different properties. So they're looking at the Earth with different glasses on. So some of them are looking at the magnetic minerals, some of them are looking at the density, some of them are looking at the elastic properties of the rocks, the electrical properties, some of them are chemistry. So there's a whole range of different properties that we can observe under the Earth. And the talk I'm going to give today is focusing on gravity and magnetics, but the same sort of logic applies to all these other methods as well. So here's another example. This one's from Mount Franklin in Western Australia, and it's an area that's primarily covered by farmland, dairy, lots of cattle. And you can see in the magnetic image, which is what we're showing here, that there's a fabulous detail of a series of linear structures. And you're just going to have to take my word for it, or rather, you're going to have to take the word of the Geological Survey of Western Australia, who have interpreted this data partly on the basis of rocks they can see at the surface, but largely on the basis of this geophysical data. And Ducomar and co-workers have been able to use these interpretations of geophysics to build maps like the one on the right-hand side, which show the relative age of all these different structures in this image. And all of those, that age determination is purely an interpretation and is based on the interpretation of the geophysical data. So the primary use of geophysics, or the first use of geophysics, let's say, in the geological analysis is an interpretive one. And we can look at other features, and this is a granite intrusion in Western Victoria in Australia. And this is we can see that there's this sinusoidal feature going down through the data. This is actually a paleo channel in the Volta Basin in Ghana. We can look at these long linear features, dikes, which are molten rocks that have come up along fractures in the earth. We can see many of these in different orientations. And then these funny curved things are the limits of sills, which again, molten rocks that have inserted themselves along bedding planes. And this nice example comes from the basin in Mauritania. So many parts of the world have this data now, and it's regularly used to help explore for minerals, but also as a primary mapping tool in areas where rarely it's either difficult to access or is covered by other materials. In the case of Mauritania, significant parts of this area are covered by sand dunes. So we're looking through the sand dunes to see what's going on beneath. But there's a problem with all of these interpretations, and there's specifically a problem when it comes to trying to automate these interpretations. And that's an idea which I haven't put the word up there. There's this idea of finality, which is this concept that you can get to the same final observation or final feature by a whole series of different alternate processes. And here we see a whole series of different linear features. Some of them are straight, some of them are curved, some of them are single, some of them are multiple. And you're really going to have to take my word for it that this image, this circle of geophysical data, mag data here, is from stratigraphy, and this is from Mount Isa. This is the example I just showed you of faults from Western Australia. These are some folds from the Northern Territory. This is the Paleo Channel in Ghana. This is a pluton, another granite in Northern Territory. Some lava flows that went down a river channel in Victoria, the sills and the dikes that we saw in Mauritania. And finally, some sand dunes that have actually 100 million year old sand dunes that have been preserved by being overlaid by volcanics, and they produce this patterning in the magnetics that we can interpret in terms of these paleo sand dunes. So there's a whole series of different linear features, which some of them are straight, some of them are curved, some of them single, some of them are multiple. And so when we're looking to try and interpret the data, we often use other forms of geophysics to try and improve our interpretations. Or, of course, if there's geology outcropping at the surface or drill hole data, we can use that too. But it's a real challenge for automated techniques to analyze or to interpret these systems because there's so many possible solutions for roughly similar features. And there are two ways we can solve this. We can solve this by applying various data analytical techniques that improve on some of the old systems. And we can do it by using more than one type of geophysics at a time, which helps to narrow down our interpretations. So just to summarize that first part, there are regional geophysical data sets which supplement direct observations in many parts of the world where outcrops are few and far between. And we can use classical, I'll say, geological methods to interpret these based on our experience and based on our understanding of the fundamental properties of the rocks that produce these different signals. But they do, however, remain interpretations which, if possible, need to be tested in the field. So let's move on to the next topic, which is feature semblance, or how we can search for recurring spatial patterns in our data. And we can think about this as the game of concentration or memory, depending on where you live, where you lay out a whole series of cards after you've shuffled them. You make sure that none of them are visible, and you turn over cards in pairs until you can find a pair, and then you can remove it from the game. And of course, this is about finding similar patterns in amongst a whole range of many different types of patterns. And so what we've been doing is developing a system that can group together all the similar patterns in such a way that a geologist can then compare those patterns and try and better understand what's going on in their area. And this sort of work has been going on in one form or another for many decades now. So for 60 odd years since Paul Huff made his patent. And one of the things I like about this patent is that the system starts off with a television camera, then goes into some electronic circuits, an oscilloscope, another television camera, a magnetic tape recorder, and then finally goes into a computer. So it's an incredible combination of analog and digital systems that were used. And the aim of this system was to try and extract straight line features out of images. And straight line features in geological images are often faults. Of course, they're often roads. They can be many things. And so as an example, I'm going to put up what is actually the first Landsat image. So most of you will be familiar with the series of satellites that have been going up now for 50 odd years, which are called the Landsat satellites. And this is literally the first image that they ever acquired. It's over the Dallas-Fort Worth area. And it's made up of pixels, of multiple bands, of different wavelengths of light. And this image is a processed image that combines some of those different wavelengths. And you could use a Huff transform to look for linear features. And if you look for linear features in this image, you'd probably see straight river sections, which may or may not be related to geology. And you'd certainly see in some places there's some roads going through which are pretty linear. So again, we have the same problem that just looking for linear features is only picking out one type of feature, but it's also not necessarily picking out the features we're interested in. Not that long after, the first geophysical images of the type that I showed you in the first section were being produced in CSIRO, who took, and you can see it says physics Landsat. In fact, this is magnetic data. They took the software which had been developed to process Landsat data, to image Landsat data, and used it in 1978 to produce magnetic images. And so now we have the ability, using Huff transforms and similar types of analysis, methods for extracting particular geometries of features from satellite images, but also from airborne gravity or magnetic images. Here's an example of a paper by E.J. Holden from UWA, who used not the Huff transform, but another transform to look for circular features, because circular features in magnetic data are possibly related to porphyry copper. And we can see here that this technique has found many, many features which are circular or subcircular, which is good, but at the same time, it's probably found too many features. And so just using the magnetic data on its own is not sufficient to be able to say which are the true positives and which are the false positives, as is often the case with image analysis. So what I'm going to show you is Leo Portis's work. All I did was provide the geophysics and ask the question, I guess. And here we have two rectangles of geophysics overlaid over the geology map of Western Australia. The one on the left is the magnetic image. The one on the right is the gravity image. And we can see just roughly that there are correlations between the two types of data. And This data is made up of pixels that are about 450 meters, and we're dividing up the entire area into very small tiles, which you can see there's one little tile. This little black area shows you the size of the tile of 40 by 40 pixels. So we're taking these two areas, which are the same area viewed with different lenses, dividing them up into 40-meter pixels, and then we're going to analyze them. And the way that we analyze them is using a process called Howlick texture feature encoding. And the way that this works is that we take a grayscale image, so that could be gravity, magnetics, satellite data, any single band of satellite, and we look at the spatial relationships between the gray levels. So we can see that all of the red dots are showing us where there's 0 next to 0, all of the orange dots where there's 0 next to 1, the yellow dots 2 next to 2, and so on. And we can convert all of those observations into a gray level co-occurrence matrix, which has the same number of rows and columns as the number of gray levels in our original image. Our original image had 0, 1, 2, 3, so 4 gray levels. And so this has 4 rows and 4 columns. And what we put into the cells in this array are the number of occurrences of each type of relationship. So there were 2 red zeros versus zeros, 2 orange zeros versus ones, and so on. And then we can rotate the grayscale image around 45-degree angles to get a quasi-isotropic gray level co-occurrence matrix. It's not perfectly isotropic, but it's pretty good. So what we then do is we've gone from something which has an image the size of whatever area we're looking at, we've turned that into this co-occurrence matrix, and then we're going to perform some statistics on that matrix. And so we're going from a 40 pixel by 40 pixel image, we're now reducing that to the statistics on the co-occurrence matrix. And what that means is that each pixel in the image, or each image, is reduced to 13 of these statistical measures. And so some of them are very, very obvious, the sum, the average, the variance, the entropy, the difference of the variance, all sorts of different forms, but they're all fairly, none of them are out of the world in terms of calculation, and they all actually get calculated very quickly. So this gives us a 13-dimensional space, and there are many different ways that you can try and represent 13-dimensional space in 2D or 3D to make it easier for the geologist to deal with. And on the left-hand side, we have what is often used to try and do dimensionality reduction, which are principal component analysis. And this is a paper by Tom Horrocks, who looked at a nickel deposit in Lapland in Finland, and he plotted the various parameters which were characterizing unaltered and altered minerals. By altered, it means that it's interacted with a hydrothermal fluid, so a hot fluid. We can see that it's separated out the orange from the black somewhat, but there's a lot of overlap where there's both orange and black in the same space. There's another method called t-SNE, T-distributed stochastic neighbor embedding, which in his example does a much better job of separating out the unaltered from the altered rocks. And so what Leo did then was to take this approach and apply it to our geophysical data. And here he did it jointly on the gravity and the magnetic data for the same area. Currently, we're looking at the gravity t-SNE plot. And there are two important things to note about this. Is one, that these axes are no longer real-world geographic axes, and two, that this is not a map of Australia. So what this is a map of is variability in those 13 statistical parameters based on the co-occurrence matrix, based on approximately 1,600 gravity tiles. And we've done the same thing for magnetics And we've also, in the example I'm going to show you in a minute, done the same thing where it takes the 13 parameters for gravity, the 13 for magnetic, so you end up with 26 parameters replacing a 40 by 40 pixel cell of information. And what's plotted here is not just a dot, it's actually the original image that came from that data. So if we can zoom in to this, and this time we're looking at the magnetics, and we can see that there's a whole series of features that as geologists we can interpret as being mafic dikes, so they've got a particular composition, and they have a particular magnetic characteristic, which I won't worry about too much here. We can see that there's not much correlation between the gravity and the magnetics in this case. But if we zoom into another area, wait a second, we can see another type of linear magnetic feature. But in this case, the gravity signal is also quite linear and matches spatially where the magnetics is. So we've got two different types of magnetic feature, one of them which shows a strong correlation with gravity and the other one doesn't. So what this approach has enabled us to do is it enabled us to separate out a huge area of Western Australia into domains that have similar gravity and magnetic characterization. And then as a geologist, I can zoom in and say, okay, this has picked all of the areas with this particular magnetic characterization and gravity characterization. So I can interpret them probably in a similar way. And of course, here we've just done it with gravity and magnetics, but there's no limit to the number of different types of data that can be simultaneously interpreted. So this idea of feature semblance is quite powerful because it's not data-centric. We're not just looking for straight lines. We're not just looking for circles. It's no dependence on the prior assumptions about geometry. It's taking the geometries that we see in the data and is separating them out in such a way that a geologist can then zoom in and try and understand better and make a better interpretation rather than just having an interpretation on one feature. He can try and make an interpretation on a whole series of features, and it can be applied to any type of gridded data at any scale. So you could apply it to SEM data in a scanning electron microscope. You can apply it to satellite data. And as we've shown, but I'm not going to show here, it can work in 3D. So you can apply it to the results of 3D geophysical inversions to try and separate out what the classes of inversion that are produced by this type of modeling enabled. So we'll move on now and we'll go to the final one. And in DARE, it would be kind of a shame if we weren't trying to apply a direct machine learning approach to understanding 3D geology. And this is some work that actually started before DARE, but has been continuing once DARE goes on. And it's answering that question that I know has been haunting many of you, which is why cats are easier to invert than geophysics. And this image here at the top, I have to waste a minute of your time to tell you about. It's an experiment that was carried out in Paris in the 1890s because there was a huge controversy over whether cats were breaking the law of conservation of momentum, because they were able, when dropped, to rotate around and land on their feet. And there was a huge argument as to whether the person dropping the cat was spinning them slightly unintentionally. I'm not quite sure how they resolved this, but in the end, it became apparent that no, cats, by cleverly rotating one part of their body and another, could actually rotate without defying any fundamental laws of physics. But what we're really talking about here is a different type of cat. We're talking about these cats. And as reported by CNN, there are estimated to be 6 billion images of cats indexed by Google. I mean, it's CNN, so maybe it's only 3 billion cats, but it's still a lot of cats. And as a result, when you feed an image of a cat into Google image search, it will 100 times out of 100 give you a whole series of cats that look quite like it, because it's got such a large labeled data set, because apparently an awful lot of people have loaded up pictures of cats to Instagram and said, hey, this is my cat. If we compare that to geology, it's not so good. There's about 700 images in Google image search if you type in the phrase geological folds. And a fold is a bent series of strata in a geological formation. Here we can see a nice fold. This layer comes around and then it's been bent and it goes up the other way. And this is, we can use that to infer the tectonic orientation of the deformation, what depth in the crust this was taking place, all sorts of fun things. But we only have 700 images, and some of them look like this. And you go, doesn't look very geological, and I'm certainly not seeing any folds. And as far as I can tell, the algorithm has picked up on the fact that these are rocks from the moon, which is why there's a policeman there guarding them. And we've got some nice folds in the curtains. So using with these sort of machine learning algorithms, if we don't have the labeled data, becomes a challenge. So what we did is we used a software package that was developed a long time ago. In fact, it was my master's thesis, to build a massive, which means more than 1 million model training set with randomly assigned parameters. And the Noddy software is a package that you define a geological series of events. So I have my geology, and then I folded it, and then I put in a fault, and then I put in a dike. And for each geological unit in that volume, we are predefining geophysical, petrophysical properties, like the density of each layer and the magnetic properties of each layer. So therefore, we can forward model the gravity and magnetic field that was a result from 1 million different randomly generated models. And here's some of them. So on the top row, we're cycling through 100 of these models. On the left, it's the gravity field. In the middle, it's the top surface of the volume. And on the right-hand side is the magnetic field. And you can see sometimes the gravity and mag correlate very well, and sometimes they look quite different. And that's because the different geophysical fields are measuring different properties to different depth extents. So we have this 1 million models, and there's the first work we did with this was a paper by a visiting scholar from China, Zhang Gao, who used a convolutional neural network where he inserted the images of the magnetics from 30,000 of these randomly generated models, where we know what the answer is. We know what the answer is because we generated forward models of 3D geology, and therefore we could simply assign a label to each type of image. This is not the only way you could build 1 million models. You could build them using a much more sophisticated physics-based 3D modeling package. But the trouble is that when you use sophisticated physics-based 3D geological packages, they take significantly longer than 15 seconds to calculate the model. And so if the model takes an hour to calculate, clearly you're not going to be making 1 million of them without chewing up some major computer time. These ones, 15 seconds a model, if you've got access to a large number of processors, you can churn out a whole suite of new models in a few days. So we trained up the machine learning system, convolutional neural network. It took about a day to train, but then any image that you took from the data set, it could instantaneously tell you not just what the typical structure was, but the fundamental parameters that went to make up that structure. And we also used it to apply it to real-world geophysical data. So this is a bit of geology from the Hamersley province in Western Australia. This is the magnetic image. On the left-hand side is a 3D model that we built. This is a 2D section, vertical section through a 3D model that we built using this convolutional neural network. And on the right-hand side is the 3D model we built using the geological data available at the surface. And so these were independent verifications of the model. It's not a very complicated model. One of the challenges with this is that if you try and do this for very complicated geology, the million models is not nearly enough. So even a billion models is probably not enough. So we probably need to include that first elicitation step, which is what I talked about in the first part of the talk, where I said, I can look at this and I can say, I'm pretty confident that's a fault and it's been cut by a dike. And if we can narrow down our range of possible solutions like that, then we can build on the bespoke training sets. So if we only need 30,000 models, it really doesn't take very much time at all. We can build bespoke training sets that can then be applied to the specific area we have in mind. And that's work that we need to start doing in the future, is building a workflow that starts off with manual interpretation of the geophysics, goes through, builds, based on that manual interpretation, builds a training set, and then applies it to the geophysics to get the 3D distribution of rocks in the area. So machine learning, the conclusion is that machine learning in the geosciences for this type of work needs labeled data sets, but everybody's too busy looking at cats. So we're exploring the potential of non-physics-based 3D modeling to provide large, arbitrarily complex, time-aware 3D models and their geophysical responses. And in between that is the idea that expert elicitation is going to be fundamentally necessary because of the high dimensionality of the 3D space in terms of the different parameters that are available to define the deformation. So conclusions, we've started to move beyond simple searches for characteristic anomalies in geophysical data to integrated geological geophysical interpretations in 2D and 3D. So that's the Haralek-Tisny work. There's been an explosion of machine learning techniques, and some of them may one day be useful, but it's probably too early to say. And many countries, Australia included, provide the fundamental geophysical data sets freely. So we have a huge publicly available data set that we can use either to train ourselves in interpretation or to use as fodder for the methods that we're developing here. And I will leave it there and stop sharing. Thank you.